Hi, my name's Doug Elson. The group that we are working with was the DripCrimp team. The purpose of our group this semester was to test a crimped head on a drip irrigation system. It's a patented product that our community partner came up with to solve the problem of water lossage in residential as well as commercial applications. We had 3 groups involved. There was a tensile test group, there was a performance metrics group, as well as a pressure testing group. The purpose of the 3 groups was to validate the design and to deliver a document that the community partner could use to take the product to market. My specific group was me, Luke Tew, Gabby Bavard, and Anna Bailey. We worked on the tensile test, and let me jump right into what's behind me. I have 3 figures and the problems that we address and the results. This is a diagram of the crimped head. This represents the crimp, this represents the emitter, and this represents the spaghetti tubing. We wanted to address the problems of dogs and pests pulling off the tops of the heads of the drip irrigation system, and also people tripping over it and then the head pulls out. So one of the things, the purpose for the whole crimp was to keep the head on in the case of a pressure difference or someone pulling off the head, and we were testing what load it would take with a crimped head and a controlled head to see the difference in the force involved. The way that we chose to test this was to use a tensile test machine. We clamped the crimped head on the machine, and it slowly adds a load to it until there's a failure and then it stops. It also is able to give you data in a Excel format so that you can then compile the data on your own time. The graphs that we were able to come up with was a load versus displacement graph, and this small curve represents the control. And we were happy to find that all of the 6 trials that we performed all reached a common asymptote with the load. It was around 30 to 36 pounds of force, and the control was 15.6, so we were pretty happy. It was a 230% increase in the tensile force displayed, and our most happy result was that in 4 out of the 6 trials, the spaghetti tube actually stretched before the head popped off. So that means that when you use the crimped heads, when something grabs it or if something's pulling on it, it will essentially the crimp will work better than if you didn't have one, because it's going to stretch instead of the thing just popping off. So we were really happy with that. We're really happy with our results and what we were able to do with the group. So yeah.
Hi, my name is Andrew Hudson, and I'm one of the team leads on the water consumption team. And the purpose of our experiment was to take the DripCrimp and basically see how much water it's going to save. The design of the product is to keep the head emitters from coming off of the drip irrigation system. So, we're going to take that model and compare it to what's going to happen when the heads are coming off and you're just, spraying leaking water all day. So what we did to do that is we set up, for the procedure of our experiment, we set up an array where we have 6 spaghetti tube lines coming from water source at constant pressure, and for the first part of the experiment for our control, we had 6 drip irrigation emitters, and we turned them on and just let them spray into the bucket. And then we repeated the experiment with 5 emitters and 1 headless tube that would just spray the water in without the emitter on it. And then the experiment again with 4 emitters and 2 headless tubes. And we had difficulty keeping the time limit and then the total volume of the water coming out constant for each of the trials of the experiments. So our focus was to look at the amount of water coming out of the headless tubes and then compare it to the total water coming out of the entire system. So for our results, for the control test, we ran it for 7 minutes and 35 seconds. The total volume was 1.19 gallons. and then the average volume is 0.199 gallons per head. And so the rate of water coming out of their heads was 9.4 gallons per hour. Then we ran the experiment again with one head off, and we came to, for 7 minutes and 21 seconds, the headless tube released 5.08 gallons, and then the 5 emitters released 0.877 gallons, yielding a total volume of 5.957 gallons, meaning that the headless tube contributed to 85% of the total water that was used. And then the rate was 48 gallons per hour, which means we were dumping water 5 times as fast as if there were no emitters, or if all of the emitters were on. And then for 2 heads off, we ran it for only 3 minutes and 59 seconds because the buckets filled up at that point. So that's how fast the water was coming out. And the headless tube dumped 8.04 gallons. The 4 emitters dumped 0.354 gallons, yielding a total volume of 8.394 gallons of water. And the 2 headless tubes produced 95% of that. And that rate was 126.4 gallons per hour, which was 13.5 times as much water as our original rate. Meaning, if something as simple as only a third of your heads are coming off during in your setup, you're spending 13 to 14 times as much in your water bill.
Hello, we're the pressure testing group. I'm Brett Huber.
And I'm Matt Hansen.
And the other 2 members of our group are Crystal Corrette and Caitlin Staub. So for this test, we needed to test at what pressure the drip crimps fail, and that's because we want to know that the crimps can withstand the pressure of an unregulated house. And so what we did for that was we wanted to make a system that would be able to vary the pressures as we wanted it to be in order to test the strength of the drip crimps. The attempts we made were, first we obtained a pressure booster from our mentor, but sadly it didn't connect to the system we had. So next we obtained a pressure restrictor that restricted the PSI to 25 PSI from the 60 that you get out of this hat. But with that we weren't able to accurately measure the pressure and vary it.
Looking back on this project now, we realized that we need to change how we're measuring our pressure in the system. Right now we have a system that just measures it on the end of the faucet. We need to find a way that could measure it through the poly line to be way more accurate when we're actually using the system. And then for our future test, by materials that were given to us by our mentor and community sponsors, we can use our pressure booster, but we need to be able to find a way that new adapters that go into the pressure booster, which was our problem in the first place, weren't able to connect our hosing straight into that, so we weren't actually able to use it for regulating our pressure from the faucet. So we can use our half-line inch from the faucet and then go straight into the pressure booster, but we need to find an adapter that will hook up to the straight quarter-inch poly line, and that'll go straight to our DripCrimp system. And that's how we're gonna next semester